Hi everyone, my name is Carter, and today we're going to be discussing the Z-effective nuclear charge chemistry. I'll talk about the theory and the calculation in a quick crash course. Let's get into it. So Coulomb's law tells us that protons and electrons attract each other. It also tells us that the further away two charges are, the less force they have on each other. And we know that two electrons tend to repel each other. So when you have an electron that's closer to the nucleus, like this one, and then there's another electron that's further away from the nucleus, you can say that this electron that's closer is actually shielding the electron that's further away. And that's because there's actually attraction between the proton and this electron. There's attraction between the proton and this further away electron, but there's actually repulsion in between the two electrons, the one that's closer and the one that's further away. This is the idea behind the Z-effective nuclear charge. It's the charge that an electron feels while taking into account any shielding from inner electrons that are closer to the nucleus. Previously, we talked about quantum numbers and how each row in the periodic table actually represents a new principal quantum number n. So this is n equals 1, n equals 2, n equals 3 for each of these rows, and so on and so forth. If you don't remember this, I've linked the tutorial about quantum numbers in the description and at the end of this video. Note that these D group elements actually have quantum numbers that are one less than the row number. So in this case, this is the 3D group of elements, even though n equals 4 for this row. And if you don't remember this, you really should see that video in the description. We've discussed all of these kind of trends for orbital numbers in that video. The effective nuclear charge is simply the atomic number of an element minus the electrons in all the previous principal quantum numbers. And we'll do some examples coming up right here. So here's how it looks for carbon. Carbon has an atomic number of 6, which means it has 6 protons and 6 electrons for a neutral atom. Of those 6 electrons, 2 electrons are actually in the n equals 1 principal quantum number shell, and 4 of these electrons are in the n equals 2 quantum number shell. You can tell this by using the periodic table. So here you can see n equals 1 for this row, and there are 2 elements, so you have 2 electrons that are in this row. For this row, n equals 2, and we've got 2 in the s orbitals, and we've got 2 that are in the p orbitals. But all we care about are the electrons from n equals 1, because that's the shielding row. And the way we calculate the Z-effective charge chemistry for carbon is we look at the total nuclear charge, which is 6, because carbon has an atomic number of 6, which means 6 protons and 6 electrons in a neutral atom, minus 2, which is the number of electrons that were there in that first row. And so the total Z-effective nuclear charge for carbon is 4. Another way you can actually figure this out is by just writing the electron configuration for carbon. So that's 1s2, 2s2, 2p2. You can see there are only 2 electrons that are in the 1s orbitals, and the remaining are in the 2 principal number, 2s2 and 2p2. So these ones are the ones that are going to be shielding. These ones will not be shielding. And so, as we had previously discussed, the Z-effective nuclear charge is the total nuclear charge minus shielding electrons, which is 6 for all of the electrons, minus 2 for just these 2 shielding electrons, which equals 4. If this electron configuration is hard to understand, you really need to look at those videos in the description. I'll teach you very easily how to find the electron configuration for a given element. All right, let's do the same calculation for selenium over here. Selenium has an atomic number of 34, which means it has 34 protons and 34 electrons for a neutral atom. The easiest way to approach this is to actually write out the electron configuration, which is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, and 4p4. If this electron configuration doesn't make sense, once again, please look at those videos that are in the description. So what we see here is that there are only 6 electrons that are in the n equals 4 principal number. The remaining electrons are all lower principal numbers, and so they're all going to be shielding. The effective nuclear charge in this case would be equal to 34, which is the atomic number of selenium, minus 28, which is the sum of all of these green electrons, which equals 6. So that's our total Z effective nuclear charge. The Z effective nuclear charge is incredibly important to understand because it teaches you so much. Just take a look at this image here. The effective nuclear charge increases as you go towards the right, and it decreases as you go down. The reason it increases as you go to the right is because you're actually increasing the number of protons that you're adding without increasing the number of shielding electrons. And the reason it decreases as you go down is because now you are adding more and more of the shielding electron rows. And this is why you have the trends that are listed here. First, there's electronegativity, which tells you the tendency of an element to attract electrons. Fluorine is the most electronegative atom, and that's because you can see here it's all the way to the right of the periodic table, and it's all the way to the top of the periodic table, which means it has the most Z effective nuclear charge with only 2 shielding electrons from the 1 principal number. Electron affinity is the energy change when you add an electron to a gaseous atom. And in this case, electron affinity also follows the same trend because of Z effective nuclear charge. And then there's ionization energy, which is the energy that it takes to remove an electron from an element. Fluorine, again, has a really high ionization energy because it has a lot of Z effective nuclear charge. Another cool trend to notice is the radius of atoms. You get larger atoms as you go down, and you get smaller atoms as you go to the right in a periodic table. And this is because your Z effective nuclear charge is increasing as you go to the right. So your atoms are getting smaller. Those electrons that are on the outermost valence shell are getting pulled closer to the nucleus and being held there. As you go down, you're actually getting less Z effective nuclear charge because you're adding more of these shielding electron rows. Electrons that are on the outside can be further away from the atom because they're getting shielded a lot. Hence, you get larger and larger atoms. And that's it for this episode. We didn't really discuss Slater's rules for Z effective nuclear charge because I wanted to keep it really simple. Make sure you like and you subscribe so that you can not only support this channel but also keep learning organic chemistry with me. We'll discuss Slater's rules in a future episode. This is Carter signing off.